basically, statically typed means that it's checked at compile time, so you eliminate a whole class of errors during runtime, right? So in this program, right, we have a C program here, and we're trying to add 2 integers, it looks like, right? And we see that in the first line, that's okay, that's how we want to use it. In the second line, we're trying to add 1, the integer, to basically a constant character array somewhere in memory, right? So it's a pointer, really. And because there's a type mismatch, we say, hey, you're trying to add this integer to this pointer to a string without casting it, into something that we like. We just eliminated a whole class of bugs there. That's why it saves us time. Typically, if you wrote a program like this in JavaScript or Python, right, depending on your settings or where in the code, you might go for like several hours and not know why like your computation didn't work out. And you're just gonna have to hunt for it and almost do like a little binary search to figure out where the bug is. So that saves you time. Functional, code is data. You can sling functions around in code as easily as any other values. You can abuse this and it can make your code pretty unmaintainable, but also it can simplify things, right? So this style lets us operate on whole data structures as opposed to just pieces of them at a time. This is why you hear a lot of functional programming people be like, it lets me express my intent more clearly, because you can really enact on the whole thing instead of just, I'm going to take this element, do this, take the next element, do that. You kind of make a big swoosh motion and just affect it all at once. So here we, in JavaScript, ES6, whatever you call it, you're mapping the element into the value, which is element times 2, right? And that just happens across everything. And then we're reducing it. What does reduce do? Well, we start with the base case, 1 in this case, and then we're like, okay, we're going to have something called an accumulator. It's a value that gets threaded through the whole list. You can think of it that way. And you pop in the new element, you start with the base case, and then you do the thing. You multiply it. So in this case, we're going to multiply accumulator to lm, meaning that we're going to do the product sum of this whole list, right? So that's a lot of meaning in just 2 lines. And if you can read and write this, right, then you're really compressed, what you have to say in kind of a clear way. You're not hiding in loops upon loops. Some programming languages, you need 100 lines to do this. So maybe not 100, but like there are many lines, variables, subvariables, maybe 2 loops here. So it really helps clarify your intent when you can pass this function and that function to affect the data structure in some way. Immutable. So values do not get overwritten or else you get yelled at, right? Because in mathematics, for example, a lot of things are immutable there. Basically, it's very nonsensical to say x is 5 and x is also 6, right? Maybe you have some kind of weird number system where that's true, but in general, that's kind of nonsense. So by sticking to that, we can just have saner outcomes. Again, in JavaScript, we see immutability by declaring a variable as constant, and it's trying to reassign a value to it, and it's like you can't do that, right? But the great part about statically typed languages, as we talked about before, the compiler is going to pick up on this, that you try to change that and just not going to let you do it, right? And that saves you a whole bunch of time, because what if you change the value of pi or something mid-flight? That's not good. Okay, so immutability reveals one interesting thing in computer science, in that it tells us the difference between caching and memoization. So caching is basically having a Redis instance or something in memory, and you're fetching a variable from the database, maybe a very expensive operation. You want to retrieve that later, right? So basically, you'll just keep it there, and you'll grab it. We'll have a cache expiration of 5 minutes, so we'll make sure that the data is always fresh within 5 minutes, right? Many of these systems like Redis let us do that, right? So that's hoping that it's there, and going to fetch it if it is. Whereas memoization has more constraints around it. You can only memoize things if we have something called referential transparency in a function, meaning that same stuff goes in, it means same stuff comes out, right? That's the property we like because it's nice and pure, as some people call it, referentially transparent, right? So basically, if I have a mathematical function, if I'm like, x plus y, 1 plus 2, right? If I give 1 and 2 to that function, x plus y, it should always return the same thing. Otherwise, my system's completely inconsistent and it's really weird and I don't like that. So basically, once we have this sort of referential transparency or immutability in a function, then you can do memoization instead of caching. And that's amazing because caching is one of the tough problems in computer science, and you don't really have to deal with that because you're always sure that the lookup will be correct, so long as that's the previous code you had, right? Cool, so lazy. Basically, evaluation is deferred for as long as possible. This means we can have things like infinite lists. Why? Because you only evaluate as much as you need, and then that's it. So we see this in some other languages too that have support for series and things like that, but this is implemented at the language level. And you can do some pretty convenient things. For example, if I don't want to use a while loop, right, and I just want to listen forever, maybe I can just pass the infinite list to map, and it'll just keep on doing something, right? So basically, the analogy is you don't start cleaning your apartment until the doorbell rings, and then only clean the parts that people can see. That's Haskell's philosophy on execution, unless you kind of add a stickler in there to force execution sometimes. This is actually a weakness in Haskell too, in my opinion, because you're gonna have difficulty diagnosing performance issues if everything is not just aggressively evaluated, right? So you might find that like during your critical performance path or something, there's this whole they're called thunks, these pieces of code that eventually get evaluated. There's a whole series of them that didn't get evaluated. So you hit that, and now you kind of have to massage the knot out of the code muscles before it can start running quickly again. So another thing about Haskell, a lot of people think it's like only for PhDs, like that kind of thing. Not really. Just get into it. You don't need category theory, abstract algebra, or graduate algorithms to use or understand Haskell. The best way to learn it is just to start reading the code and writing it at your level, like whether that's you're starting out or you're trying to learn some more constructs. You should just really start getting into it. Instead of just reading about category theory, going down all these different rabbit holes that people are like, oh, you can't possibly start until you do that. That's going to really set you back a few years in terms of being able to get something and understanding too. In fact, a lot of the times you'll find experienced Haskell programmers, they'll just start picking up category theory because they have just so many natural patterns to draw off of, and it'll just make a lot of sense to them, and it's going to be a widening feeling like, oh, I didn't know that was the general system, right? Like, in mathematics, there's something called groups, and in groups, you basically have a binary operator, takes two elements, right? And one of the constraints is when you use the binary operator on two elements, it returns a new element within the set, right? And wow, there's a lot of stuff that kind of fits into there: addition, subtraction, multiplication, etc., right? They're all considered groups in this field known as abstract algebra. So when you hear about a group, you're like, oh wow, I didn't know, the pieces fit together like that. So I would use that analogy to category theory, abstract algebra, or some like mathematics to how people think about Haskell. But you really don't need to know what a group is to just add 2 plus 2. You should just do it, and then through practice, you'll kind of understand how you can zoom out a bit. Cool. So let's talk about functional programming in general. So we're looking at object-oriented style, right? You would have something, an object, of course, because everything's an object in most object-oriented languages. And I want to drop, let's say, the first 3 elements, right? Okay, makes sense. Now, in functional programming, we'll usually start with the function, hence functional programming. Drop 3 to this, right? We focus on the functions because it's functional programming, whereas object-oriented focuses on the object. So that's pretty clear-cut to me. But let's zoom in a bit. Basically, instead of asking what can this function do with this prefixation on the object, we're closer to asking, what can I do, right? What are the set of functions I have to work with? These are the tools in my tool belt, kind of like the Unix command line. And then, okay, what can I operate upon, right? And composability is what you get out of this. Because if I just learn what map does, and map is my trusty tool that I use in many situations, right? All the things that kind of look like they can be mapped over, right, like lists, I can just reuse map. In fact, there's even a data type or a type class called foldable, right? And you can do things like fold on it. Fold is Haskell. You can think of it as Haskell's implementation of reduce. So basically, if we just fixate on these functions, the action over the actual thing, it saves you from diving into these, crazy Pojo files I'm sure you've seen before that just have a million accessor methods, and you have to wonder what the hell can this thing do, right? More like, what are my capabilities? Okay, and what's the universe I'm operating on? So that's kind of the transition. Okay, so getting started, I'm just going to walk through this. You can do this on your own time, just optimizing for your time. So you will install something called stack which just is basically a whole suite of utilities that brings in the Glasgow Haskell compiler, named after the University of Glasgow, which is where it's developed. Brings in Cabal, which is the package manager, and a bunch of other stuff. It's kind of like a quick start pack, and it is probably still the best way to just begin learning right now, although that ecosystem is evolving. So you can basically Stack will vendor your binaries for you. So it's going to download the latest GHC into somewhere, and you can run Stack's GHC instead of your system's GHC, and it solves a lot of problems for you. So basically, this is what a Haskell program looks like, the traditional hello world. Main, now main has type of IO, and we send basically an empty tuple to it. This means that we have input and output. And this is a nice feature of Haskell in that if it's outputting to the system at all and affecting changes to the rest of the world, generally from the type signature you can already tell. So that means when you run like a pure function or something, right, that doesn't affect the system at all externally, then you know, because you can just read the type signature, and that makes things a lot safer. Contrast that to, like, I don't know, even Go is kind of bad at this in that, like, you can just erase the whole file system if you wanted to in a Go function, right? Import OS, and you can do like os.rm or whatever the command is, and delete the root directory. Same thing definitely for Python and JavaScript. You can do that as long as you import the sys library or whatever else in Node. So like it's really interesting of even a secure coding perspective. Like I can write a function, and based on the type signature, right, of the interface, the programmer cannot affect the system in any way other than, you know, adding more CPU cycles or something. So that's pretty powerful. Excuse me. So basically, let's look at a slightly different function, sales tax. It takes, we'll get into how to read the signature so it doesn't look so scary down the line. This scares a lot of people off because it's just weird. It borrows a lot from the type inference studies and, you know, advancements in research. So basically, it's pretty straightforward. Sales tax on a variable input parameter price, right, is the price times whatever the tax rate is in Georgia. And like that's calculating the sales tax. And if we see that, we can compile it and just run it on 100, and we get 8.9. Okay, importing modules. Looks a lot like Python's import. In fact, we even have the selective import, so you can pick specifically what you want to import. So data.char will just import everything from data.char, but if we import data.char, just the function ord, right, order, like, so give me the ASCII value of this character is basically what that function does. We can do that, and just like some other languages, you can do a qualified import, which basically renames this into its own namespace that you can access within the program, c.ord. We'll call the same function. And that's just sort of the Python analogy, in case you're familiar with that language. Within GHCI, so GHCI, the I stands for interactive, GHC is the compiler, and you can basically import libraries, and it kind of nests you in to show you that, okay, you're within this new scope, and you can access things there. Great, so let's start with some basic Haskell types. Before that, any questions so far?
If you're working in GHCI and you wanted to import two, what does it? It just keeps growing the.
It does.
The font? Yeah. Okay.
Yeah, you can import a bunch at once though, and I think avoid that. But yeah, it can get a little ugly. Okay, cool. Basic types. So one really big thing that I don't see in too many tutorials that's going to help you get unstuck a lot in Haskell is just remembering that types start with a capital letter. And variables, including functions and type variables, start with a lowercase letter, right? That's just a general truism. I can think of many cases where it doesn't hold true, but in general, that's your first suspect. So look at these types, right? They all start with the capital first letter. And if you're familiar with programming languages at all programming languages tend to have types. You know, even JavaScript, right? There is such thing as a type error. It's just not checked at compile time. So let's go over what the types are baked into Haskell in the beginning. First, we have int. It's a fixed precision whole number. Depends on your system, what precision they choose to use. Integer is an unbounded whole number, so there is big num support by default, just like in Python and Haskell. And like it's actually really nice because if you're trying to just write the crappy version of some kind of cryptographic algorithm or something, and you have a really large prime number, and you don't care about performance, you can just kind of like use that, you know, and just get a proof of concept correct before you try and tune it. Float, single precision, floating, double is double precision floating. Bool is just true or false. Char is a single character such as a. And going on to a little bit more complicated, we have a list. And the thing to know about lists and functional languages in general is that they looked a lot like a traditional linked list as opposed to an array that you might find in C. An array in C, for example, is just a nice kind of like packed data structure, right, with all the elements next to each other or close to that in many languages. And you can kind of predict based on the memory location where the next one's going to be, right? In functional programming languages, predominantly Lisp, Haskell, this kind of family, like they like to do this thing where it's actually, like you have the value there, but also you have the pointer to the next element, just like in your singly linked list, right? This is because of one, history, and also I think it's just easier to do some operations as opposed to reshuffling your whole array. If you're working with lists a lot, you might appreciate this as your default, but I think the rough kind of transposition might be if you look at maybe a JSON object in JavaScript, right? Instead of just packing our values in an array, it's kind of like we have the value, then we have the next one, right? Which is its own like little unit. It's kind of like a pointer. And then we have the value of the next one, and finally there's no more value, right? So that's kind of how to look at these lists, which means some operations are pretty inefficient, and you don't really want to use this for intensive processing, but it does have nice properties, such as being able to, again, insert something in linear time, as opposed to just having to shuffle everything again. So I'll tell you also the functional part of the list and why it's like that. It seems a little weird at first, but basically this is syntactic sugar. And it kind of stands for like a list of numbers in Haskell, right? But really, it's a function composition. And there's this kind of a cons operator, constructor, I think is where it's from, where it's a dot dot, and it means that take an element and append it to the beginning of the list, right? Because if you think about how a singly linked list works, right, you always want to insert at the beginning. Because if you insert an n, you have to crawl through the whole list O of n, and it's going to take you a while, right? So basically, this operator starts with an empty list, which you can think of as kind of a constant, and it will start to build adding 3, prepending it, and then prepending 2, and then prepending 1 until you get that. So every time you see this, under the hood is a bunch of function calls actually building out your list. Because again, it's functional, and this affects pattern matching, which unlocks something we'll see later. So basically, heterogeneous lists, meaning different types in the same list, very easy in dynamic programming languages like Python and JavaScript, not so easy in Haskell or any other like languages with kind of strong type systems, I call them. Because if you ask many Haskell programmers, they'll just respond with, why would you ever want to do that, right? There must be something going on. Why don't you use a different data structure or something like that? But it's just not something that people like to do here. And also kind of an anti-pattern in Java is if you have a list of objects, right? And you're like, what can I, because like basically a type direct in a statically typed programming language, a type blesses whatever variable you have with what it can or can't do, right? And if all you say is object, then you've just limited that universe to really small. Like what can you do? Find its reference and that's it, right? Until you know more things about the capabilities of this object through its type, it's really impossible to get any meaningful mileage out of it. Okay, so let's just go through some list operations because that's always a good place to go next. So let's take the first element with head, like kind of like the head of a snake or a dragon or something. You want the first one, right? Head of this list is 1, okay? And if we take head of an empty list, then of course it explodes. You can have runtime exceptions in Haskell. There's the statically typed compilation doesn't always save you from that. There's an operator called index, and we get to pick various elements from a list by index. And we can also check the presence of an element with lm, right? And because we know how a list is structured, we can kind of guess at the runtime of each of these operations. Reverse is going to be horrible, right? Because like basically you have to transcend the whole list before you can actually start reordering the thing. Adding two lists together, so concatenating them, right? You can imagine an implementation that uses the cons function that we saw earlier. We can even take a few elements as we saw before. And lastly, well, before we go to fold, any questions?
So on like Elm, does that short circuit if it finds the thing?
I don't know that implementation detail, but I imagine it would. So mapping a function across a list with map. So basically, let's define a function. Let add 5 x equals x plus 5, right? We'll get into the syntax a bit more later, but I think I hope this is understandable enough for everyone to work with for now. So we have a new function. We feed it x. It gets plugged in. And it's always funny how they tell you to never say that, but it's like such a useful term in my professional career anyway. So then you can map this function over this list, and the function gets applied to every single element, right? So we get 6, 7, 8 because 5 was added to each of these integer-like things, right? Now, if we have a fold L just means that we start folding everything together from the left side, right? And whereas fold R is from the right side. Basically, we need to give it another function, right? Let's say we want to add the list up. How do we write the fold for that? Well, we give the base case, which is 0. We want to just start from 0, right? And then we also, over here in the first parameter, we have to pass it a function. And basically the function goes like, okay, give me like what you have so far, add it up, give me the new thing, and then this is how you merge them together to get the output. We add them, right? Because we want to sum it. So 0 is going to go to the accumulator, right? The element's going to pop in. It's going to basically add 0 to 1, right? It's going to be 1. And then 1 is going to be the new accumulator. 2 is going to pop in. We're going to add those together, get 3, right? And then 3 is going to be the new accumulator. And finally, we're going to add 3 to 3 and get 6. So that's how fold works, just like reduce. Cool, any questions? Great, moving on. So tuple. So you might be familiar with tuples from Python and some other languages. Basically, you can have different types as elements in your tuple. That's one important difference, right? Whereas you can't really do that very easily with the list. There are some convenience methods for accessing pairs, which are just two tuples. That is, tuples with two elements. We call them pairs. FST is get the first thing. SND means get the second thing, first and second. So if we have a 3D point, we can define it like that. Tuples can even be nested, right? So we can have a string over here. Germany lives over here. That's a lat long. And if we want to access what country it is, if we're using this kind of data format, we just use FST. If we want to access the second value, which is a pair in itself, we just say SND.
Just to be clear, for a tuple, you can have each element in a tuple can be of some type. It can be of any type.
That's right.
But for each tuple of some type of tuples, if the first one's an int, it always has to be an int, right? So if you go to like to use your example for locations, right? You say, I'm going to have a bunch of locations. A location is a tuple, first element of which is a string, second element
That's right.
which is a tuple of, I don't know, float and float. Or...
Yep, so if we're making a list of tuples that can be, nested pretty deeply or whatever, the tuples all have to be of the same structure with the same types in the same places. Because again, you can't change the type from element to element in your list. So, yep. Cool, good. Cool, tuple, moving on. So, actually, there's something called an associative list, which is a list of tuples, and you find this a lot in functional programming, just because it's really easy to do this. As soon as you need like a map for something, right, you have to like make a hashing function or something like that, and it gets kind of messy, so traditionally programmers hacking on, the old time sharing machines like to just have something really easy to access. And you can define it really easily, as we said before. Notice how this list is now of type string int, right? Because it contains tuples that have the first element, which is a string, and the second element, which is an int, right? And we kind of put the brackets around it to indicate that this is a list type. So basically, we're defining a variable eating contest scores. It's a list of tuples, right, of that type. There are some given, I guess, like preconceived functions for you, such as lookup, that will just like kind of parse through this and conveniently give you an output. So tuples are of different types when they vary in size or constituent types, right? So again, if we're making a list, you have to just choose one of these and roll with it. Cool, moving on. All right, so this is sort of the meat of the presentation and what you should really take away from this hour or hour and a half that we're together. Basically, you have to be able to read types if you're trying to write in Haskell, where everything will look really scary and make no sense whatsoever. So basically, this double colon can generally be read as has type, right? And it's more of a declaration than an observation, actually. So basically, we can say that 5 has type int, right? And the compiler's like, okay, that's okay, you can do that. And then we can do 5 has type integer. Remember, this is sort of the big num, unbounded kind of integral value. And then finally, we're like, 5 has type string, and the compiler is like, you messed up really badly. I can't like make that work through my axioms and type rules. Yes?
So for like your list where you're saying you can't mix types, what about like int and integer, like since int is a subset or...
Yep, so we'll get to that a bit when we cover type classes briefly, but rather types can belong to a type class, right? Instead of using the type, you can use the type class.
Right, so
which,
you could say number and...
Yep, and we'll get to like how a type can belong to a type class and what you can do with that. Cool? Cool, so another thing is the function operator, or function arrow as some people call it. It denotes a function that takes an argument of the type on the left and returns a value of the type on the right. Okay, that's the clearest way to understand it. This goes in, that comes out, right? And what in particular, something of that type goes in, and something of this type comes out, right? So that's exactly how you have to read the arrow. And basically for this example, right, we can kind of just try and pattern match it. Add 5 takes in a value of type int, right, and outputs a new value of type int, right? So that holds. Let's take a look at something a bit more functional, something called a higher order function, which itself returns a function or deals with them. So make adder. What if we wanted to make a whole bunch of these things, right? Is there a way we can do that using a function instead of just writing it out all the time, right? And the short answer is yeah. Basically, with this function, we can look at the type signature and learn a lot about it already. So we take in an integer, or an int rather, and we return this type signature. Basically, that function, right, which is a function, takes an int, returns int. So we take in an int and return something of that function's type. But it's not necessarily add 5 because we didn't define that yet. It's whatever this value is. So let's look at the implementation of the function, the definition. Basically, make adder x, right? It's just going to replace, this is an anonymous function over here, right? And you can read this by, this is a function that takes in y and adds y to x and returns that output, right? So just know that we're returning a function and not an actual int, because you can tell from the type signature. And this definition works recursively. So basically, again, just to wrap it up, like make adder, we are constructing, we can do add 3, add 7, whatever, right? I think I have the example here. Oh, no, I don't. But add 5 can just be defined as make adder 5. 5 goes to x, 5 is kind of, you can think of it crystallized into x here. And now we have a new function that takes something, plugs into y, adds it to 5. Good as add 5. It's logically the same. Cool. Any questions? Great. Let's practice some more on reading types and how Haskell will process the types. So basically, we're going to import data.car. We're going to import a specific function from there called toLower, right? And what type is it? Well, toLower has type of a function that takes a char and returns a char, right? If I have a capital A, it's going to be a lowercase a stays a lowercase a, underscore doesn't know what to do with it, probably gives me an underscore again, right? So basically, we want to invent a new function. Again, composability is key here. So how do we do that, right? Well, we want to map, let's say we want to do it over a string, we'd want to map this toLower function over a string, right? So we have here a list of char, and then that's what goes into the function, and what comes out as another list of char, right? It makes a lot of sense for a toLower string or lower string function. And we just define lower string as map toLower. We just kind of shove toLower into map, and whatever comes after this, right, it'll just work because it completes the call to map. And we're going to get into why this makes sense. Hold on. Let me see where we make sure that makes sense. Okay, cool. So we'll get there soon. But basically, you can think of like map, takes a function that is applied to individual elements, right? And we're giving it one over there. And we're creating a new function out of that. Okay, so you can use :t in GHCI, or :type is the long version. That's probably what I should have put here. To basically ask, GHC about, hey, what type do you think this thing is? And GHC will, like any kind of mathematician, give you the vaguest answer possible that is most generally applicable, right? And in this case, we have add 5. We would expect int to int, as we saw, right? Because that's the data type we know and love. But really, we get this weird num thing, right? And this is a type class. We say that for all, A as num type class, A in the num type class, we can take an A and return an A, right? And remember what we said before, that types have capital letters in the beginning, whereas variables have lowercase letters. Well, this is a type variable that represents the type, right? So it's lowercase. Add 5, therefore, also works for floating types, not just ints. Because floats and doubles happen to be part of this num class, which defines things like addition. Cool, so let's talk about a little bit about this narrowing of the type. This is an important concept to understand if you want to kind of understand how types play with each other in Haskell, I think is the best way to put it, and you're going to combine them a lot. So here we have add 5, and we declare add 5 has type int to int, right? And the compiler checks, and they're like, back here it said num a, right, with the locking a down to the type class num, but it's like, int is part of num, and you're saying int to int. Okay, I'll allow that, right? It's kind of like if you were like, okay, this function takes a square and returns a square, right? And then the compiler is like, oh, it actually takes a rectangle and returns a rectangle, but I guess a square fits that definition, so you're cool, right? And that's fine. But the problem is, you can't ever go back up to rectangles because you already said that it has type square to square, right? You can't kind of zoom out again. You already locked it down further to int, which 1.2 cannot resolve to, right? So it's going to explode on you and give you a bunch of complaints. Any questions? Cool. So currying, other than being delicious, I know everyone hates when people make this joke, but it's obligatory, I think. But it's the process of transforming a function that takes multiple arguments into a function that takes just a single argument and returns another function if any arguments are still needed. So it's kind of a mouthful, but I think examples will be the easiest way to just kind of go through this. This is kind of the uncurried function call. Basically, you can look at it like this. I'm trying to draw resemblance to the C, C++, and Python functions we all know and love, where you just kind of write the parameters, you give the parameters. If you don't give enough of them, the compiler is like, hey, you didn't give enough of them, or the interpreter yells at you, right? It's one of those things. But basically in Haskell and other curried languages, a curried language meaning that it gets curried automatically, the functions in it, basically you can imagine functions like an onion. And you can just kind of unpeel layer after layer until you get this beautiful expression evaluation inside, right? And that's kind of the ultimate form. So when we define a function like this, and so if we don't put one of the values, it's just going to kind of complain. But here we can define add xy equals x plus y. This is kind of the natural way to express a function in Haskell, right? And what we can do is something called partial function application, where we just plug in one of the values and we just let the other one float and just be free, right? But now what happened is that we just, instead of creating a final value here, we just created a new function where you can plug in the other thing and then finally get to the conclusion where you can take no more values, right? So that's what currying is. It means that you can think of this automatically turning into a single function that takes only one argument, right? It'll just do that over and over again until you actually evaluate the expression. So these are some more examples to just really get it through. So again, this is kind of like in an uncurried form, I guess. Some pedants might have problems with how I expressed it, but I think it gets the idea across. Basically, you need to fill out those two variables for the function to make any progress or make any sense or evaluate at all, is my point. Basically, in the first curried form, right, it's what we said. Let's look at the function type. Let's look at the function type for the uncurried, right? It's kind of like a tuple, a pair, right, of int results in an int. Unless I get this full value at once, I'm not going to do anything, right? Whereas we look at curried, right, you can pass me this one, and then this one, and then this one. Take your time. You don't need to do it all at once, right? And this one's the output, actually, so it's only two. So let's look at the second one, which kind of means the same thing, because when we pass in, when we put a value, when we apply a value to add, right, it basically fills in x, and it takes the space of the first type in the type signature, right? So we kind of knock this one out, right? And then when we come with y, it knocks out the next type, and finally we get the int that we wanted, right? This can also be expressed like this, where add x equals, this is again an anonymous function notation, where you pass in x first, right? It knocks out the first int and returns you a function which takes int and returns int, right? Which is exactly what this thing is. And then from there, you can again just knock off the next one and basically get your final evaluation, right? So you can apply this over multiple stages, that's totally fine. And finally, in the most extreme form, we just define everything with anonymous functions, and we just see that the parentheses don't make a difference in this evaluation. And from that, we can kind of draw the conclusion that the right arrow operator is right associative, meaning that this stuff happens first, and you kind of unpeel it like an onion. Now, the beautiful symmetry here is that function application is left associative due to currying. So it kind of cancels each other out, and you get your final value that way. So let's just go through this again. Like, basically, as we saw, we can keep on stacking up the parentheses. By the way, this function signature can be moved there, and I think it would be okay with you, because it logically evaluates the same thing, right? So it's right associative by default, this arrow operator. And it's actually operating on the types themselves. And this is where some of the mind-bendy Haskell stuff comes out. Basically, these are equivalent, right, as we saw. But in order to unravel that, right, these must also be equivalent. In that the thing closest to the function, right, gets seeded to the first item. Then that returns up another new function where you feed it to the next value, right, b here, and it bumps out the next one, and then finally C, and hopefully you get a value, right? So because we have this symmetry between the associativity of these operators, you're able to come to a full evaluation. Cool. Any questions?
Is there any time that in coding Haskell real world that you would do something like take something that only needs something in the num type class and then go ahead and define it, basically the equivalent to go ahead and lock it down? So you could say add ints.
Yeah.
Like that.
Yep. Some people are pretty stringent on code hygiene and just getting as much as you need to the type, right? And you don't want to expand your scope any more than that. Especially useful when you're dealing with like protocol layer stuff, where you have a bunch of like int32s that can match a num, and you want to make sure this is only an int32. Then the compiler can help you out there.
I got a question too. So
Yeah.
the querying, so it sounds like the order of the parameters matter. Like you can only kind of replace in one.
That's right. Yeah.
Okay. So you can't like choose to, like replace a third or the second variable. It has to be the first one each time. Okay.
That's right. Yeah. Lisp will have a very similar kind of layout too. There are actually 2D and 3D programming languages, but those are pretty esoteric. So let's go to our friend map again, which we probably see a lot in JavaScript and Haskell and Python now. Although I don't think that, what was his name, Guido? He doesn't like lambdas being multi-line or whatever. Anyway, so we have the two-lower once again. And we want to figure out what the type of map is, right? And, okay, what does map do, right? And again, this is something to just take note of. The type signature tells us a lot about, what kind of person map is, right? Basically, we see the first parameter we take in is a function that takes an element, takes a variable of type A and returns a variable of type B, right? And notice the parentheses. They're necessary. They're not redundant because, again, it's right associative. The arrow is right. So in order to cordon this, to say that this is actually a function, we need the parentheses. So why is it A to B and not A to A? Well, we might return something different, of different type than the original value, right? What if I have like a list of lists, I'm trying to count each list and be like, how long is this one, right? That would be a function from list to int or something like that, right? Because I'm trying to get the count out. So we want to allow that. Or it can be the same thing. A can be equal to B, and that's fine, right? It's just we're deciding where we want to give freedom to this function using these type variables. So next up, we have, that's the first input, right? A function from A to B. And now the next input is a list of A, right? And conceivably, we run the function on each element of the list of A, and we get a list of B. And that's basically the type signature for map. Any questions? Very cool. So basically, if we look at the type of two-lower, right, it's char to char. And if we partially apply two-lower to map, right, knock that first thing out, and get a new function, we get this char to char. What happened to A to B, right? Like, what the heck? So let's figure out how it did this calculus. By calculus, I just mean moving things around, more or less, not like specifically like with real numbers or something. Okay, so Hindley-Milner type inference is the magic behind this in a lot of type systems that can evaluate like this. And basically, it's just a search function. It figures out, can we like match up the type variables to real concrete types, as some people call them, in some meaningful kind of way, right? And basically, we pull up the char to char function, right? And it just kind of, you could probably write this routine yourself. Basically, like, we see is there a match, right? It's like, okay, let's brute force it. Let's see if A is char and B is char. Do we still have a consistent logical system, right? Are we stepping on any toes here? And lo and behold, if you substitute char for A and char for B, right, we have no conflicts over here. And we can just chop this part off because it cancels out, right? And if you actually look at the literature for Hindley-Milner, you'll see that there's a weird notation that does this exact thing. It tries to knock out types and reduce them. Basically, at the end of the day, that's what we're left with. And therefore, that's a type signature of the partially applied function. Any questions? Cool. So basically, just some examples to show you that we can change the type of the list, right? If we want to see if things are even or not, right? We just kind of apply even to a list of ints, and it'll tell us which elements are true or false. This is especially useful for things like, these are especially useful for data processing, although I would say numerical computation isn't Haskell's strong point today. But if you look at a functional paradigm, some cool languages like APL and J and K that are used on Wall Street quite often, they're called array languages. They take this functional paradigm and allow you to apply it to a high dimensional matrix or something, right, all at once. And then you can take the average of it or something and reduce the dimension. And that's all, you know, happening in a functional way. So like this kind of like paradigm where you're just kind of mapping over entire data structures instead of trying to pick out the element, open the nut, eat the thing, and then, you know, put it down, do the next nut, and you just kind of have a generalized form for all nuts all at once and let the computer figure out how to order it, right? That kind of frees you up to think about other things, and you're not going to make rookie mistakes forgetting like a, you know, a swap variable or something like that working that low level. When you're writing a web application or a financial application or something sophisticated, like you don't want to be thinking about memory allocation, right? So by the same means, these are some pretty powerful tools that free up your mental space as a programmer. So reading type classes. Basically, types can belong to type classes. And you can think of interfaces in Java or Go. But basically, again, the compiler is going to help us pick the most generic expression of this function. And how does it deduce this type class? There's not too much magic. It just so happens in the type class definition for num, we see the requirement for a plus operator, right? And it must do some things, right? And from that, the compiler can infer that at least it must be this num thing, right? Int implements num, so does float, and all these other types, they all implement num. So it can be any of these things. Let's just go with the most generalized version. Okay, so if you only have, remember when I was saying that like types are kind of like, if you have object in Java, it's kind of useless unless you just want to like get reference or something like that, right? So same kind of thing. Basically, the only function that you can implement with a single type variable is ID, which simply just returns the function, it's the input variable itself. There's a wonderful paper called Theorems for Free, where I forgot who wrote it. It might have been Philip Wadler, but basically, by reading type signatures and combining them in different ways, you can prove some theories in your programming languages for free, like get free functionality out of your programs. It's not too mathy. It's more like, you know, you can figure out what these things do, or you can combine them in a new way. Because again, if we have the constraint that we have, you know, only if we have this type constraint, I think there's only one possible function that you can write with this type of function, and that's just returning the thing itself. There are no other possibilities, right? And same kind of thing here. Like there's another function called swap, which it's like AB goes to BA, right? And there's really only one implementation you can do, because you can't like form anything on those. They're just kind of types. You don't have a plus or anything. You're just a free-floating type out there, right? So rearranging it is the only thing you can do. So anyway, just giving you some function examples with type variables so you can get more familiar with them. First, it can be any type A, any type B. They can even be the same type. You're just returning to something of the first type. Another theorem for free, so to speak, because there's only one way to implement it. Head, there are many ways to implement head, but the one we know and love, it takes the first element or explodes. Take takes, you know, n elements and returns you a new list with them. And zip is something that you'll see a lot in functional programming. Very useful. We were talking about associative lists before. Well, it makes one for you. It basically takes two lists, maybe of different lengths, and like a zipper, just zips up to the shortest list. And basically, the elements from you know, one list is joined into a pair with the corresponding element from the other list. And you can do really interesting things with this, like if you're just trying to like add two lists, like if they're kind of like on like the elements directly with each other, you can just map like a plus b over this, right? And you can just do that. Or you can even like, what if you want to do something like, if I have two numeric lists and I kind of want to add them like that, right? But I want to shift one list over, right? And add to the next thing for every element, right? Imagine how much boilerplate you have to write in like C or something to get that to happen. You need these false start indexes and all that stuff, right? Whereas in Haskell or some functional programming languages, you can just kind of truncate and take, instead of head, there's something called tail, which will just give you the rest of the list, right? And you can just kind of run the same function on that. So it's a very powerful expression. It saves you a lot of, picking through the seeds as a little bird or something. A weird analogy, I know, but that's sort of how it makes me feel. And like, working at almost this assembler level kind of abstraction. Cool. So some examples of type classes. That's what we're talking about. Basically, we can write a perfectly good function like this because we know num empowers us with a plus operator, right? Which can do different things depending on the type implementation of it. But we can write something called sum, which basically folds a list together of num-like values, and it starts with 0 because 0 is part of the mix, and or like actually, you might want to, I don't know, I have to check the definition, which is on the next slide. But anyway, that's the general idea, that you can start wheeling this plus in functions already. Go ahead.
If you put a function in parens, does that make it intex?
Yes, that's a good point. We'll go over that soon.
Okay.
Yep. So basically, these are some other expected operators from different type classes. For eq, or the equality types, you want a double equals implemented. For ord, or the ordered types, you want a less than. And guess what? If you have a less than implemented, then and an equal implemented, then you can get a greater than for free, right? You can just kind of implement that generically. So num, let's look at it. Yeah, it looks like 0 is intimately tied to this type class somehow. We need to implement these operators, but what's interesting is, okay, well, if you didn't implement minus, well, we have a default implementation for you here. So long as you implemented negate, we can just add them, and that should mean minus. So if you follow this kind of consistent idea, then you get that for free, basically, and that's really convenient. However, there like one note of caution I might make is that like there are ways that you can implement like plus and negate, so that your definition, the default definition of minus is wrong, so to speak, because like not like that you follow this logical system, this algebra that they have laid out, right? That's like something that comes from you, the programmer, and not necessarily checkable by the compiler. So you just have to give a lot of thought into, like, there are some additional axioms to actually making a numeric type that is just too annoying to put in the compiler. And you as a human just has to be more careful and think it through, like, okay, so is it consistent? Does that implementation make sense? Is my minus implementation different? Is that wrong or right? I'm just saying there are additional concerns here. We can't always trust that that's going to be right. Any questions? That was kind of vague, but I didn't want to go into detail there. Cool. Okay, so another type class is show, and most types that you come stock with Haskell will implement show. Basically, it turns into a string, right? So most things implement that. What else? Yes, so as we mentioned before, because we have this type class, right? This type class show, we can be sure that anything we pass into there can be showed, and show just converts it to a string, right? So that's convenient if you're trying to write something that prints things, and most types will implement show. Cool. So infix functions. Go ahead.
One thing that I made the mistake a few times is that where it says instance show int, where as Wayne said, the show and the int are both capitalized, meaning that they're types, right? Whereas just below it is the word show, which is not capitalized. That's a function, right? So I've hurt myself a couple times with that.
Definitely. Yeah, I have a lot of pains too. I have some of them in the slides too that I'll go through for everyone. So hopefully you don't make the same mistakes I make either. So basically, infix functions are like that. Infix meaning they're infixed in between two of your inputs, right? What type? ABC, meaning that they can have one thing on either side. In this example, the first 5 goes to A, the second 5 goes to B, and then we get C as the result type, right? If you look at the type, that seems to be the case. Because we're in this like 1D language, right, line by line, you can only kind of do it like that. There's no like elements, above or below like chessboard or something. That's not how it works in this language. So you can also summon or call these infix operators as normal function calls by just surrounding them with parentheses. And speaking about symmetry, you can also use a normal function that's not an infix function as an infix function if you put backticks around it. So for example, the mod statement, the mod function modulo, it's very convenient to put between two numbers because it actually looks closer to the equation. It just boils down to the same thing. The infix function support's actually quite good in Haskell. You can decide if it's left associative or right associative or kind of like non-associative. And you can also decide the strength of the associativity, so order of operations, right? I believe the higher the strength, so up to 9, like level 9, the more the more the compiler wants to do that first, right? So you can create your own like algebras or whatever, your own mathematical systems with their own orders of operations. So it's quite flexible. Okay. Anonymous functions, we already saw many examples of these, but I figured I'd formally introduce them and the thinking behind them. So as we discussed, there are what was it, 2 hard problems computer science, off by 1 errors, caching, and then also naming things, right? So basically, for anonymous functions, this avoids one of the toughest problems in computer science, naming things, right? Because, like, kind of using the theory that, like, we only want to, get to know the tools really well if they're useful to us and generally applicable, right? We don't want to learn these one-time use objects. We want to, like, have a really nice tool belt that we just reuse all the time, right? Basically, if we have this one-time function, we don't even want to give it the brain juice to like come up with a name for it, right? We just kind of want to use it once and get rid of it, and that's totally fine. So what if add 5 is not something I do a whole bunch, right? I didn't want to think about should it be addition 5 or add 5 or 5 more, right? It's the tough thing that I want to do. So basically what you can do is an anonymous function using the backslash operator. Why backslash? Because it kind of looks like a lambda. That's the only reason. So there are some text editors that will actually make it a lambda, but that's just what it is in Haskell. You don't have to think about it. That's basically it. So if you see the backslash, then you know there's an anonymous function being defined somewhere. They can get kind of hairy, so you might have to break it out after a while.
Can they be multi-line?
Sorry?
Can they be multi-line?
Yeah. You just have to indent it further. Yep. And white space does matter in Haskell. We'll get to some error classes that you can get there. When in doubt, use parentheses, or you can look up the infix strength. Okay, so 2 scary things you'll see in Haskell. These are like operators. These are functions. You'll see them just nested in code, almost like poets use commas and like exclamation marks. Like, well, that one's literally a period, but anyway, like basically you'll find these sprinkled across code, and if you don't think about what they do, or you don't know what they do, code gets really confusing because you're like, okay, it kind of makes sense. That's the function name. These are the parameters. But what is that? Why did you put that there? Like, are you sure that wasn't a mistake? And basically, this is what they do. So it's this dollar sign here is known as application, and dot is known as function composition, right? So this dollar sign calls the function, which is its left-hand argument, on the value, which is its right-hand argument, right? So basically, this is the value, right? The right-hand argument in its entirety, and over here is the function, right? This is the function, calls, which is the left-hand argument. It gets called on the other side of this thing. So math add 5 is actually the function, right? This whole thing gets called on everything here. So this fully evaluates and we get a value out of it, which is going to be 6, 7, 8 as a list, because we add 5 to it. And then we can add 5 again, right? So that's all it does. You'll see it sprinkled because people don't want to make it look like Lisp. They don't want to add all these parentheses. That's really one of the key reasons, I think. And now this dot is the function composition function, and it basically is a higher order function, just like that one. It composes the function, which is its left-hand argument, on the function, which is its right-hand argument, right? So more straightforward. Basically, you might have seen f.g in like algebra class or something. Same kind of idea. If we want to first double something and then add 5 to it, right? It's the same thing as add 5.double. We've just created a new function. You can even throw it into a variable if you want. Cool. I see this application used far more than I do composition in code. Okay, so one pitfall that you have to look out for is mismatched arguments. And this means basically you always have to be thinking about what's getting passed in as like a parameter and what's getting kind of called as a function, right? Because functions can just get passed into other functions. So, you know, there's some more flexibilities here in this language. So what went wrong here? Why did we get this big scary error, right? Well, basically, and I'll go through the error message a little bit because reading them is a skill that you have to learn over time. There are actually blog posts about how to read GHC error messages. It's pretty funny. But why did it go wrong? So basically, the map function thought we were passing in 4 arguments. Add 5, map, add 5, and the list. When really what we wanted to do was first add 5 to everything in this list, take that, and then add 5 again, right? So because of that, it's like, hey, map only takes like, you know, two arguments here. What are you doing, right? And it just kind of yells at you and refuses to compile. So you can either fix that by putting parentheses or using application as we saw earlier. We just kind of dial into the error a bit. Basically, couldn't match expected type. So here's the magic. The function map is applied to 4 arguments, but its type has only 2, right? So that tells you a lot. We can work through the type signature stuff later, but definitely you'll find some keywords in here that'll give you the right clues as to what happened. And you'll see some, you know, crazy looking type variables here only because that's how the compiler figures out what works. So it might need A1, B1 or something. So basically that's just internally how it figures it out. It's kind of showing you some of its guts, to put it in elegantly. Okay, so pattern matching. Any questions about what just happened there though? Application, composition, cool. Moving on to pattern matching, and this will be the last topic. We'll probably spend 10, 15 minutes on this, and then we'll be done and we can hang out and talk about Haskell or whatever you want. Pattern matching is an extremely useful technique that is a staple in functional programming languages. It allows us to search for the data we want from an expression. We will cover pattern matching constants, lists, and tuples, and using pattern matching in function definitions, guards, where, let, case of. These are basically the constructs you'll see over and over again that give you your control flow in Haskell. Whereas you have like if statements and for loops in some languages like Python or C, In Haskell, you have if expressions and like switches and things like that that always evaluate to expressions. We'll get to them soon. But the one thing to always remember about pattern matching that's going to get you unstuck in a lot of places is that it always happens top to bottom, left to right. Okay, and that's going to make sense very shortly. Okay, so this isn't exactly pattern matching, but I think it gets the idea across, so I like this example. So basically, it's called destructuring is the real term, right? They're actually trying to introduce pattern matching into TypeScript, but anyway, I digress. So instead of doing this thing, right, where you're like trying to pick out the thing from the object every time, right? What if in one fell swoop we can just deconstruct this data structure and get the stuff we want out of it, right? And by how do we do that? Well, we just basically, you know, use the fields as the selectors basically, and just siphon it out of user, right? And we can just do it all at once. So this resembles pattern matching, although it is not pattern matching. And we'll get into some real examples of pattern matching now. Okay, so basically, this is a function definition. It's not an exhaustive function definition, but it's a function. And what this function does is if you guess 5, it returns true. If you call the function 5, call the function with 5 as the input, it returns true. But for all other cases, it throws a runtime exception because we just didn't find what happens then, right? And this is the power of pattern matching, because we can basically say over here that, you know, for that case, it's true, right? But we didn't say anything else about the other cases. What's cool about this is that the compiler, because of the type system, can tell us if we're missing some stuff, right? So it can deduce from this pattern matching definition we set up that, hey, like we know the universe of possible int values, you only check that one, right? And you know this before you run your program. So that's really useful. You have to turn the warning flag on, but it's always a good option to have it. So how do we fix this, right? How do we make 5 the only correct guess? Basically, you add an underscore, which means I don't care. Match on anything, right? I'm not even going to use the value, just throw it out. Basically, this will catch the rest of the cases. So anything top to bottom, right? We're going to try and hit up 5, and if that doesn't work, we're going to go to the next one, and that's just the catch-all that returns false all the time, right? Okay, cool. So let's implement map. We've been, you know, deconstructing its type and everything. Let's figure out, you know, how to implement map. Now we love recursive functions in functional programming languages, functions that call themselves, right? Conveniently, these pattern matching paradigms are very, very easy ways to have a straightforward implementation. Let's just walk through this, right? We're already familiar with the type signature, right? We take a function that takes A and returns B, and the input's a list of type A, and we output a list of type B, right? And A and B can be the same again. So that's the declaration. Let's look at the definition. Basically, map takes 2 parameters here, right? Takes an F, which should match up to that type, right? And therefore, we'd expect the second parameter to match up with that type, right? Hold on, what is this sort of like colon thing, right? Well, this is pattern matching on a list, right? Not just any list, but a list with at least one element. Remember all the way back when? Oh geez, I'm not gonna go there, but like basically 1, 2, 3 is expressed as 1 colon 2 colon 3 colon empty list, right? That's how it was expressed. And basically that's how we can destructure or pattern match on a list with at least one element. Because if we feed a list into here, X becomes the, I guess like the earliest element 0, XS gets the rest of the list. So this type is going to be A, this type is going to be list of A. And this is really convenient because we operate a lot on lists in Haskell and other functional programming languages, and we can just start using this stuff in our code. So how will we use this in our code? Well, we're going to apply the function we just got to that first element, right? And then we're going to prepend it to the application of map, using the same function on the rest of the list. So that's a very clean implementation in my opinion, because you're able to just pattern match over here and find that. But what about empty list, right? Because empty list can't be pattern matched like that. There's no element to go into X. It's just XS, which would be empty list. In fact, that's what happens when you only have one element in your list. The only element goes into X, and then you get an empty list in your XS. So basically, we're going to process the list all the way until it's grinded down to that empty list, and then again, top to bottom, you could actually do this either way. You would just return an empty list because there's nothing left to do. And this one would just always get called at the end. And also Haskell does have tail call optimization, which means if we end on the same function itself, it'll do a very tight loop for us instead of trying to just call the function and grow the stack. Cool. And one more little trick is if you see this @ symbol in front of it, basically you've asked for a handle to the whole list in addition to the pattern matching. So you can use that. Any questions?
Is it more efficient or less efficient, or who cares, if you put the map F of empty list as the first pattern to look for?
I would think, I don't know actually. I think that would depend on how the compiler implements it.
Okay.
Yeah. I guess it depends on usage too.
So the search is top to bottom?
Yes. Yeah, because if you're always searching the 0 case and you get non-zero lists for most of the cases, then it might be better this way slightly. But I guess it doesn't matter unless you're doing it a lot. But
I was thinking in C, when you do your switch statements, you're like really trying to optimize it. You figure out which ones are called the most, and you put those at the top of your switch statement. I would assume it's.
And then like I just had really bad flashback to like the go-to statements in the switch cases, which people like to do. Really scary stuff. But yeah, that's nuts.
Is there fall through?
Fall through.
Yeah, like like in a switch statement in C, it'll just keep
Yes.
falling through. Like so, it matches this, or
Oh yeah, so there's no continued execution. No. That's one of my favorite things about Go actually. Like by default, it stops at the end of the case, and you actually have to type fall through to get to the next one. I thought that was a major failing of C, but. It's a fun one. So, these are some mistakes I have made. Basically, it's very tempting to put the brackets around it because it's like, oh, list type, list. No, that's not how it works. You get a very confusing compiler error. You need the parentheses. You can't just go without them. Just the AST doesn't work like that. The syntax tree, the parser. And the last one's okay. So pattern matching is the only way we can use values in tuples. So if you ever deal with coordinates or anything, you have to use some kind of pattern matching to get to the stuff inside to use them. Here are some examples. Basically, we are pattern matching in this function definition here, right? We want to basically take the Euclidean distance of two coordinates, right? 2D coordinates, and return the double of the distance. So in order to do that, oh, by the way, great feature of Haskell, because it's very inspired by things in math, you can add a single apostrophe to your variable name, and it's just part of the variable name. Kind of like x prime, because that's kind of the notation that mathematicians like to use. It's pretty useful when you just want to be like, oh, I just changed the variable a little bit, and I changed it some more. So you'll see that a lot as just one of the cultural things in Haskell. So anyway, so the pattern matching happens right here at the function definition level, right? So if we pass in, the first one, the first pair, it'll get matched to x and y. And it'll already get you the stuff inside the tuple. The second tuple will be x prime and y prime. And then we just have the distance formula there. Cool, and it even works with nesting, right? If we have like some kind of weird associative list where it's like the ID gives you a tuple, a pair of the first last name, right? We can kind of just show the whole thing by having a function that pattern matches this nested tuple structure, and you can do that as much as you want. Cool. Any questions about matching tuples? Great, moving on. So guards aren't actually pattern matching, but people just throw them under this family. You'll find it in all the Haskell books and stuff. Basically, this is a way to quickly test expressions, and like you will basically get results. You can think of this as a series of like if-thens that always returns an expression at the end. So basically, this is for hot sauce, or something called a Scoville score, right? It's like, how hot is this hot sauce? And this is a variety of comedic reactions to said score. And basically, it's going to go top to bottom, right? And we'll get to the left to right part later. But basically, otherwise, it's just far above those, or at least greater than that one. Any questions about guards? The important thing to note is that it always produces a value, an expression, right? And this function would return a string, as you can see.
It always has to return an expression in
Yep.
Haskell, or always has to return a value in Haskell.
Mm-hmm. Yep, it always results in an expression. And that's an important, so here's a few mistakes that I've made. Don't put an equal sign there. It's just, that's okay, but the equal sign is going to mess you up because you're not really defining anything. They just kind of switch the syntax in this one. And also, you don't have to start right below it. You can start next to it if you just want to list it out. Again, inspired from mathematics. If you ever took a probability course or something, you see how the PDFs branch out, and it kind of looks like that in your kind of piecewise function definitions. Okay, cool. Pattern matching where? This stuff is a lot for readability, where being one of them. So in this example, I just wanted to show you that total compensation with all these inputs, right, is basically base plus bonus, right? And that helps us with readability of the function a lot, because when you just go in, you can see the first line, oh, it's just base plus bonus. And if I want more information, I can just dig in and see what bonus is derived from, right? So it allows you to kind of taper meaning into your function like that. I know in C, a lot of programmers do this. So I'm always in the habit of scrolling to the bottom of main.c or whatever it's called, so that I can find the main statement, so I can find the entry point and whatever happens, right? But it's very nice to be able to just put it up front like that instead of waiting for the whole build-up. So if you want to see how bonus is calculated, rank multiplier plus performance, we define a new variable here, rank multiplier, and it does some stuff, right? So basically, we can also use them to pattern match. And for here, we're showing a point, right? And we want to create these new strings, x prime and y prime. You probably named them something better, but that's what I went with. And basically, when we run show point, right, we can take in a point in P, right, and pattern match to x and y, and run the respective show functions on the variables to turn them into strings, and basically just have these this print out, x equals whatever the value and y equals whatever the value. So again, pattern matching is used in the where statement to pattern match on what's inside the pair of P. Cool, any questions on where? Cool, so let is kind of the other way around. Instead of defining things after, you just do it up front, right? So for the quadratic equation, we might have, the lovable formula kind of scattered over here, but we have the root term, numerator, denominator, and at the end of the day, the numerator goes over the denominator, right? So that's just another way that you can structure your code. And it's, again, mainly about readability. Sometimes you want to have a function that you reuse several times. If you've learned about lambda calculus before and S expressions, then you'll basically you can look at this as everything just kind of gets nested deeper, right? And you're kind of forming new nestings over here. Same with the where clause.
What do you think you see more often, the let in or where?
Definitely let in.
Are they the same? Are they just sugar for each other, or is there some?
I think they could be. Yeah, I think you can get from one to the other, and if you make an AST, but not certain.
Okay.
Yeah, it feels like it though.
Yeah.
Okay, cool. So case of. Basically, oh yeah, so this is where the left to right comes from. And you'll just so you know, so in the pattern matching case of, right? So basically, this is different than the guard we saw because usually, like in the guard, there was an expression that would evaluate to a Boolean, and based on that, we would either go with the expression or not, right? So for the case of pattern matching syntax, basically we have pattern matching at every step of the way, again top to bottom, and now we can go into left to right. So this function, we're just trying to display what kind of point it is, if it's a normal point, a y-intercept or an x-intercept, or the origin, right? And basically it had to be this order, or like you could flip these two, but otherwise, you know, the order had to stay the same because it's you know, top to bottom, and left to right, right? So we're going to try and match on the origin. If that doesn't work, well, do we have a y-intercept? Well, if that doesn't work, do we have an x-intercept? Otherwise, it's a normal point. It doesn't matter in this case, but like it's going to try and match left to right with some other statements, and you can see how maybe we could trip up in that later. So that's just an easy rule to remember. What's up?
Can you double up the match? So like right now you have like 0, 0 origin, but say like 1, 1 was also origin. Did you have to make a new line, or could you just do like 0, 0, comma 1, 1 for origin?
I think you would have to make a new line. Yeah. Okay, so one really important difference between Haskell and imperative programming languages is that they have if-then-else statements, whereas Haskell has if-then-else expressions, which are a function that return an expression, right? And basically, you can just use them like any random value because you're always sure that they're going to evaluate to an expression that you can then use, right? So even like if then else is going to have a function type, it's all sugar for some kind of function call with you know, that as an input with like what 3 arguments, right? And it'll just pick based on if it's true or not. You can imagine the function implementation being pretty straightforward. If it's true, it goes to 1. If it's false, it goes to the other. Okay, so this is where spacing starts to matter in Haskell. Basically, this is a common leaning for people coming from imperative programming languages because it looks a lot like what they're used to with if-then. This is very Python-y, right? But because we mentioned that these are kind of, this is more of an expression, right? The if kind of begins the code block, and we want to see then first option and else second option kind of contained within the same level, right? Because if you're moving the else back to the same code block as if, it's going to try and read it as something else, and you're not going to have a good time. Cool. So that kind of concludes concludes pattern matching. We can go over some types if you guys want. It'll take like 5-10 minutes, but up to you guys. Show of hands. Yes. Okay, let's go over some types. Great. So this is in Go, and basically you'll find the need to just kind of declare these different types of records sometime in your programming career. It's really surprising how often it comes up. Like, oh, what type is this? I guess it's an image type. Anytime you're building like a generic system, it feels like you're building part of like a compiler because you're like, oh, you know, what type is that variable? Oh, it's a web banner, and this one's a button that you can click, right? But they all have to go to the same system because we're programmers, we like everything orderly, right? So this might be for employee records. We have records for like person type, so employees, managers, and clients. Over here, I'm just defining a new type called person type so that basically I can't accidentally throw these into functions that accept strings, for example, right? Or vice versa. I can't throw in just a random string into a function that expects a person type. That's the only reason I'm defining a new type, to make that delineation. So are you okay, right? And basically, if you're a manager or client, then yeah, you're okay. But if you're an employee, maybe not, right? False. So and if we don't know what you are, it's like, what are you doing here? We're gonna throw a panic, right? Unknown person type, and that's the error message. So basically, again, I can't just throw a random string into here because it has to be of type person type, and that, you know, saves us from a junior programmer just kind of deciding that they will implement, you know, intern by just passing the intern string into this function, right? So type person type disadvantages. Strings are really expensive when you're trying to check if they're equal, right? Although, like, it's my preferred way. You can use enums, and that's fine, but like usually I favor readability over just you know, cutting edge performance at all layers, right? So basically they have like huge number of possibilities. You only want like 3 possibilities, but this string is telling you like 2 to the 128, and you're like, whoa, that's a lot, right? So someone can also just kind of cast aggressively into that type and just kind of violate it. I guess it's kind of their fault, but whatever. And there are no exhaustiveness checks. You can't just check to make sure all the different person types are, you know, more or less aligned without some extra tooling or something in Go anyway. So even using enums, right, you just have the whole number space of UN or something, and that's like much more than you need to actually, you know, represent like your 3 records, right? 3 different record types, I should say. So what happens if we forget one of the types, right? Well, it's just going to be unknown person type employee, right? Because we just forgot to implement this case. This happens to programmers all the time, just kind of a slip. And, you know, oh, we didn't handle that case, and now, you know, everyone has their data or something. So enter some types in Haskell. Basically, this is how we define a new type in Haskell. We use the data keyword. This is one of the ways anyway. The main way that you'll see probably. Data person type. This is a new type we're defining because basically it starts with a capital letter, right? So therefore it's a type. It's basically one of employee or manager or client. All of these can count as person types. And what are these, right? Those were just never referenced before. We just made them up right now. Okay, we're not like, we didn't define these somewhere else, etc. This is where it gets confusing because like these are actually called value constructors, right? Whereas the type rule makes it kind of weird now, but just bear with me. And basically, this is the first point of their existence right here. Again, employee, manager, client did not exist before this moment in time, or in the code, I should say. And now we can start using this type that we defined in functions. So we can say greet person type, right? How do we actually tell, you know, what type we're talking to? We can just use the pattern matching, right, on these so-called value constructors. It's easiest to think of them as constants as first. Okay. And basically, if it's an employee, good day, right, and hello manager, and we can run our main function as we saw before with hello world. And now you know what this dollar sign does, right? The function on the left gets applied to the stuff on the right. Greet evaluates client to a string, and then we print it out. Otherwise, the compiler would have thought that put string had like, you know, 2 arguments. What's up?
In this enum type case, can you namespace those under person type without like polluting all of your stuff, or?
Don't think so. Yeah. The nice part about this is that if you run GHC with warnings, it'll warn you that you didn't match on client because it knows the summation of everything that person type can be, hence some type. And when you run it, it's going to have a runtime exception because we didn't catch that. So again, you know before you start to execute, and whereas the Go compiler couldn't do this for us. Maybe you can add an extension or something, but this just comes baked in. So we add it and it's fine. Cool, so we went over sum types. That's basically that. That's the sum type, and it's the summation, or you can think of like the ORing, right, of employee, manager, client. Okay, so let's go to product types, right? So basically, sum types can be combined with product types to store additional data, right? So basically, let's say we want to define a new type called appointment time, right? And we want to have it in several states because you can not have an appointment scheduled, right? It could be a walk-in, that's fine, or it could be at a certain time, right? Now, the cool thing, so some types so far, right, not scheduled walk-in or at, right? But here's this weird thing. We have this product type, so to speak, in which, in the case of this at value constructor or constant, we see this something, this is a type now. So you can turn the weirdness detector off. It's capital U type, okay? We have something of type UTC time. UTC being universal something something time. Just it's a time type. And it only happens when the record is at, right, as the value constructor over here. They're called value constructors, and this is way later in the presentation, but I'll just tell you. They're called value constructors because after you run it, it yields a value, right, of some kind. And in this case, we get a full value with the time, whereas these, you just get no arguments, right? They're called unary, I believe. So basically, how can we use that with pattern matching, right? Well, if we want a status update in the form of a string, right? It's not scheduled, not currently scheduled. Okay, straightforward. We just match in the value constructor. Walk in. Okay, we walk in during business hours, makes sense. But in the case of at, right, we can expect this to be filled out with a UTC time, meaning that we can do anything that we can do to UTC time with this parameter over here, or this pattern matched variable, right? It's captured. And this is convenient because now you can write code that is like storing this in the database is a whole nother issue that we can talk about, and there are frameworks to help you with that. But just focusing on the application layer and being able to use this in this case, and not having this ugly thing where you have a struct, which is, maybe there's a pointer to time that might be null or something, right? The field isn't even there. Like, you're not concerned with it if it's not scheduled at some time, right? So in my opinion, this can be cleaner in many cases. And when you run it, right, we'll basically get the current time into this variable, and we will construct a value of type appointment time using that value constructor by passing it current time. And we will pass that variable of type appointment time to appointment status, right? And we will get a string as a result and print it out. What's up?
Is at like a reserved word, or can it just be anything?
It can be anything you want it to be. And also, another important thing is that, and a very confusing thing is that value constructors and like types have different namespaces. So you can also name one of these things appointment time, and that's one of the very confusing parts of the language. But depending on how you use it, the compiler will pick up the context and everything. So algebraic data types you basically learned all about through all those slides. That's all they are. Again, they're just sum types and product types. There are no divisor types or subtraction types that I know of. That's all you have in Haskell. So basically, I think that's a very good place to leave off, but this kind of gives you a taste of like the power of the type system and how it simplifies things and saves you a lot of errors. We went over some of the functional modes of thinking and also the value of immutability. So hope you enjoyed it. Feel free to just come chat with any questions or anything. Thanks for coming.
How do you use Haskell at your job, Wayne?
Writing DSLs.
Okay.
That's what it's really good at.
Yeah. I think you used to do a lot of JavaScript somehow generate JavaScript. So
You can do
write
that
a
with
nice
JS, and there's something called PureScript that kind of looks like Haskell, but yeah. I guess I don't really like working in JavaScript at all.
Yeah, it's best avoided.
But no, I thought that was how you handled it. It's like, no, there's a way to do it now.
That's it's very tempting, but every time I just don't see any libraries, so I'm like, oh, that's a lot of work. So React is the way to go.
Maybe on the case, you could have your own kind of switch on both.
Coming back soon?
Can you spell it?
Coming back soon? Sure. Okay, cool. We also have